I see that I'm always on the big screen. But so yes, today it's a turn of Matteo Corigliano. Matteo is a PhD candidate of the 37th cycle. He started in February 2022, so with an additional scholarship. He graduated in December 2020. He's a civil geotechnical engineer, and he's now doing his PhD in the geotechnical field as well. His professor is Professor Claudio Di Prisco, and in his research group there is another PhD, another a postdoc, and also an LTDA. And Matteo's topic is in the field of geotechnical engineering. In particular, he's developing new tools for the assessment of the performance of deep foundations of existing bridges. So today he will show us some simulations and some tools he developed during these years of his PhD. So Matteo, the floor is all yours.
Thank you, Angela. For the presentation, Angela. So, why talking about assessment and retrofitting of deep foundations of existing bridges? Here I reported an introductory slide with some pictures of the 60s, in which we have the inauguration of a famous one of the most important highways in Italy, and in the central picture, the construction of a viaduct on another highway in the south of Italy. And what is important here is the timeline. We can see that starting from the end of the Second World War, and in the next years, in Italy, many infrastructure were built. And at the beginning of the 70s, in Italy, there were 4,000 kilometers of highways built. So what is the meaning of this slide? To understand that now we are all the heritage of infrastructure, in particular this 4,000 kilometers is reaching the design life. And so all the heritage, I'm talking about highways, but the same reasoning can be done for railways and so on. All this infrastructure must be reassessed according to the current design standards that have changed during this long time from the 60s. And the reassessment, in particular of the viaducts, and in this special case, for this talk, we will talk about the foundations of these existing bridges that at that time were not so much considered. And this is a typical case, a typical situation of a viaduct with typical foundations used in these years. The typical foundation for a viaduct with an area of 10 to 20 meters is, for the piers, we're talking about the piers, is a foundation with a raft supported by piles. And the important fact is that the piles have a length that is similar to the measured dimension of the raft. This is a scheme of the problem we are considering. what we can notice is that the section of the pile that is reported there is light reinforced. Why light reinforced? Not because the engineers at that time were stupid, but because they didn't consider the actions induced by the earthquake. So the piles could be verified only considering the vertical action coming from the superstructure, while in the picture at the right, I reported a scheme of the foundation with the loads, the loads acting on the superstructure, considering also the seismic action. And we have not only the vertical load, but also a bending moment and an horizontal load, whose effect is fully coupled. And the main load, or the main direction of load, is the direction transversal to the axis of the bridge. So the disposition of the piles is justified by that, by this fact. So we have a viaduct, and the main load direction for the foundation is transversal to the direction of the viaduct. And what is the workflow I will follow? I will consider traditional verifications, and I will prove that the traditional verification is not good for the purpose, because it has a lot of limitation and simplifying assumptions. And for that, let's start from the question posed by the industry. That is the verification approach that we are using correct, considering that we have to verify a lot of values, a lot of foundations, so we should spend a lot of money on this. So before spending a lot of money, let's try to verify the verification approach is totally correct. So I proposed an improved verification with respect to the traditional one that is based on a lot of simplifying assumptions. And then what I will do is a generalization of this approach in order to, with the final aim of proposing a simple tool that is capable to give information on the verification of the foundation and on the possible retrofitting intervention. So the final objective of the research is to find a tool that must be simple to be used for all the foundations, but at the same time reliable and more sophisticated than the traditional approach, which is oversimplified. So, with the objective of have a simple tool, some assumptions must be done, and the assumptions are made starting from the current design code prescriptions. So the standard code is my first point to consider. And so the verification that I propose will be a pseudo-static verification. So I will not do dynamic analysis on the foundation. I have pseudostatic forces acting on the foundation that are the result of the dynamic analysis performed on the superstructure with the piers that are rigidly clamped to the foundation. So in the analysis of the superstructure, the foundations are not considered, or better, of course, are considered rigid in order to overestimate the pseudostatic forces acting on the foundation. And so in general, even in the sophisticated verification I will propose the coupling between the structure and the foundation will be considered. And also another aspect will be considered, that is the kinematic interaction, the kinematic effect induced by the seismic action on the piles. But for this geometry, the effect of the kinematic interaction is not so important, so it is a good assumption. And let's start from the conventional approach that is what is commonly done by companies for the verification of foundations. The main strong assumptions done by the companies is to disregard the effect of the raft, so of the upper part of the foundation, the effect of the upper part of the foundation, the raft, is not considered on the bearing capacity, so as if the foundation is not attached to the foundation soil. And as you can imagine, the bearing capacity of the foundation will be underestimated. And another strong assumption is that the piles are connected to the raft by means of hinges. This means that the raft connects the piles, but the raft is not capable of transmitting bending moment to the piles, so that the piles are only vertically loaded, whereas only transversal loaded, and the bending moment is absent. And going on with the traditional approach, we can, the other strong assumption is that it is considered an elastic distribution of forces on the piles. What does it mean? The meaning is that the failure of the foundation is considered when one pile reaches failure. And this is a very strong assumption, because let's imagine to have, we have to distinguish between geotechnical failure and structural failure of the pile. And it is the moment to be clear, in the sense that geotechnical failure means that the piles can't resist in terms of soil resistance, so that the soil around the pile can't resist. While for the structural failure, when I use the term structural failure, I intend the fact that the pile is failed structurally, so an hinge developed in the pile. And according to the traditional approach, the geotechnical failure of one pile means the failure of all the foundation system. And as you can imagine, it is a very strong hypothesis because let's imagine you have a raft with 20 piles, and if one pile fails, we have to consider, according to the traditional replication approach, we have to consider the foundation as failed, and so the retrofitting is necessary. It is maybe it is a too strong hypothesis. And what happens, according to the standard verification, using all these previous simplifying assumptions, is that the foundation is not verified neither to the vertical load, the vertical load center. So if we made the simple calculations of the traditional approach, we find that the foundation of the viaduct can resist neither the action of the weight of the bridge itself. And this is a nonsense because the bridge actually exists. So why, if we verify, we find that the action is higher than the resistance? This is due to the simplifying assumption made. And so the further step is to introduce more sophisticated approach. Recently, a researcher from Naples introduced a more sophisticated approach, which is capable of considering the distribution of forces on piles. So we want to have an elastic distribution, as in the conventional approach. But we have a redistribution of forces so that all the piles can reach geotechnical failure. But all the assumption of the presence of the raft that is disregarded and the hinges between raft and piles are present. So the approach is more sophisticated but still simple. And this is the verification. According to the conventional approach, we see that our design load, that is the red cross, is out from the domain, the light blue line. And there, on the right-hand side, we see that the red cross is still outside the domain, according to the plastic verification proposed by Di Laura, the plastic verification. We see that for this typical configuration of the foundation, that is typical of the 60s, the plastic verification proposed by Di Laura is not so different from the elastic approach, and this is due to the particular configuration of the piles, even if the plastic approach can be used in a proper way for other type of foundation, but it is not our case. Here just to have a more complete framework, there are 3D representation of the domain, considering also the presence of the horizontal load. And as you can see, the cross is out of the domain that is the lighter line. And then let's pass to the more sophisticated approach, that is pseudostatic finite element numerical analysis on one half of the foundation, thanks to the symmetry, in which the soil is an elastic, perfectly plastic medium, and the piles are modeled as elastic. What was the load path imposed to disrupt the verification is the imposition of a vertical load, and then after the imposition of a vertical load that represents the load induced by the weight of the superstructure, I progressively increase the bending moment and the horizontal force on the foundation. And this is representative for the seismic action in a pseudostatic way. With this approach, we can overpass the limits of the conventional approach. So the raft here is connected to the piles, really connected to the piles. We have no hinges at the pile head. So this simplifying assumption is overpassed, and the other one is the presence of the raft in simulation. The raft can pass force stresses to the foundation soil, and it is not disconnected as in the simplified approach, in the conventional approaches. And from this slide, we can understand the importance of considering the raft interacting with the soil. There, at right, we see the pushover curve of the foundation subjected only to vertical load, and we see that if we do not consider the raft interacting with the soil, we obtain a certain bearing capacity of the foundation, while considering the coupling of the raft and the piles in the soil, so that the raft is interacting, the bearing capacity of the foundation doubles. And the second aspect, so we until now understood that not considering the raft, the bearing capacity of the foundation is underestimated, strongly underestimated. And here we can see that considering the connection between raft and piles in a proper way, we can also consider the bending moment in the piles due to the load on the raft. And the important fact is that this bending moment is not negligible, but we can reach values of bending moment in the pile heads due to the rigid connection that can induce the structural failure of the piles. And this aspect is not considered by the conventional approach. And what we can conclude from the improved verification with numerical analysis is that the geotechnical failure and the structural failure of the foundation is the level of load associated to the failure is higher than the design load. So what we learned from this analysis is that now the foundation is verified from both structural and geotechnical point of view, and so the retrofitting is not necessary. And another aspect is that the structural failure happens before the geotechnical one, and a priori is not possible to know what is dominant between geotechnical and structural failure. And this is something that, thanks to the numerical analysis, we can account for. And from this slide, we can see also that with the increase of bending moment on the foundation, we have rotation of the foundation itself that are not so negligible. So we are talking about a foundation system that is connected to a superstructure, and the superstructure had admissible displacement, so the foundation can't displace as much as you want, but there are admissible displacement. And ideally, what I want to propose is a tool, a simple tool, that is capable also of accounting for the displacement of the foundations for this typical geometry. And I will develop this tool in the framework of the macro element approach. That is an approach widely used for a problem of foundations, for example, for shallow foundations. And the idea is to pass from solving a problem at the local scale to solving a problem at the global scale. So passing from local variables and the necessity of performing, for example, numerical analysis imposing the constitutive rule at the local scale, the boundary conditions, integrate all over the domain spatially. We can pass to the global scale and have generalized variables. So what we need are the displacement of the foundation calculated imposing the generalized forces on the foundation itself, and by means of a matrix that has to be computed. And this is the tricky part. In the framework of the macro element approach, I know what are the ingredients that I need, and I started from the case of the shallow foundation. It was developed, that was yes, let's say invented here in Politecnico a lot of years ago. We need different ingredients such as the failure locus, the loading function, the hardening rule, and all these ingredients. And I started with this particular geometry to find the ingredients for the macro element. And the first ingredient is the failure locus, performing a lot of numerical analysis on this typical geometry. I found the failure locus, which has this particular shape in the bending moment vertical load plane. And I also observed the mechanism happening for each direction of load. And this is something we will recommend in the next slides. And this is another section of the failure locus that has a particular shape, just to have an insight on the results of the numerical analysis. We are in the plane bending moment horizontal load acting on the foundation. When the bending moment and the horizontal load have the same sign, so we are in the first quadrant there, the domain has a reduced dimension with respect to the other one, in which the bending moment and the horizontal load have opposite sign. And this can be explained thanks to the fact that when bending moment and the horizontal load act in the same direction, I compress a volume of soil that is the same volume of soil, so that the resistance of the overall foundation is reduced with respect to the case in which they have opposite signs, so the bending moment and horizontal load are on different parts of the soil. And observing the mechanism happening at the foundation level, I try to propose simple expressions for recovering, simple way to recover the shape of these failure domains, this failure logic, by means of equilibrium and imposing the constitutive law, observing the mechanism, the shape of this failure logic is easily determined by means of n calculations. And the interesting point is that these expressions works also for other geometries. For example, until now we have considered only, in this discussion, we have considered only the typical case of the 60s of a typical bridge, but adding also other piles to the foundation, the expression, the simplified method works. And going back to the objective, that is the definition of the failure logic and the ingredients for the macro element. In our case, we need the failure locus not only for the geotechnical system, but also for the structure, because as I said before, we have not only a geotechnical failure, so not only the soil can fail, but also the pile. And so we need a failure locus also for the structure. And the interesting point is this shape of the structural domain that is rotated with respect to the domain of the soil, so of the geotechnical domain. And also this rotation can be explained, but until now I haven't found an expression to link the geotechnical domain with the structural one, but the rotation can be explained thanks to the opposite effect that have the horizontal load and the bending moment on piles, when they now opposite to what happened for the soil, when the bending moment and the horizontal load have the same sign, so act in the same direction as there, the effect on the piles is counterbalanced, so the domain can enlarge with respect to the other parts. Yeah. Before going to the next step, to the conclusion, just to sum up what we can learn from this talk is that there is the necessity of introducing more sophisticated approaches with respect to the traditional verifications, and that there are a lot of simplifying assumptions that can be overpassed thanks to the numerical analysis, but it is not all, because the numerical analysis need a verification. So the next steps of my work are the experimental validation of my results, and also to complete the framework is the introducing the information on the retrofitting, the best retrofitting. So, studying the results, interpreting the results of the numerical analysis, try to find the better solution for each situation, for each direction of load. And yes, these are the next step of the work, and that's all. So thanks for your attention.